optimization and control, which is kind of the core area I'm working in. I will probably talk for about 90 minutes or something, so there will be definitely plenty of time for questions in between. So as Michael mentioned, please feel free to interrupt anytime. This is meant to be interactive, so just keep on asking questions. And this talk is really for you. So just also for me, it helps if you ask questions actually, just to get a bit feedback of how your understanding and feeling about the talk. Okay, so I would like to talk a bit about distributed optimization today, in particular about the new type of algorithm I'm currently developing for non-convex optimization and control, which is called Aladin. I will talk about what Aladin stands for. So the main objective of the talk is in fact to find out what Aladin is, and to talk a little bit about the theory and applications. So as a motivation, I brought today a sensor network. So actually on this slide, we have 7 sensors which are placed here in 2D. So actually the task here is to find out where these sensors are. So the green dots are simply the sensors in 2D. So we have them, actually the positions are denoted by Xi1, Xi2, and so on until Xi7. And well, in the easiest case, each of these sensors just takes a measurement eta I of its position. And then in order to find out where it is, it would just solve an optimization problem, which is decoupled. Yeah, so each sensor can solve its own optimization problem. It would just solve the minimization problem and probably set its own position to its measurement, because that's the best information that is currently available. At that stage, we have not communicated with anyone else. So this is the decoupled case. Now, what I'm going to talk about in this presentation is actually the case that we have a coupling. So the coupled case is actually visualized as follows. So here we have the situation that the sensors can additionally measure the distance to their neighbors. So for example, this sensor 1 here can measure the distance to sensor 2, and they can communicate about what their relative distance is. Yeah, so there's an additional measurement available. And now, we see we will build a network here. We have a very simple circular network, but it could look more complicated. There could be many more sensors in general. And what we see is already for such simple identification or location problems, we get non-convex optimization problems, which are coupled in general, and their structure very much depends on the network topology. So here in this case, the maximum likelihood estimation problem, which we would like to solve, is a coupled nonlinear optimization problem. So it's still a least squares optimization problem. Yeah. So here's the decoupled term. So this is the term which comes from the sensors itself, measuring their position eta I. But then we have this additional term here. So the distance between Xi I and Xi I plus 1 is actually measured, and we have this eta I bar here is the measurement for the distance. And actually, if we look at this optimization problem, so it almost looks like a standard convex least squares problem. But if we look at this carefully, it is actually not. Since we have the norm here, so this is the 2 norm, so here's really not the square missing. There's no square at this norm. Yeah. So since this is really the distance, and the distance is measured, and then this whole term here is squared in the objective. So it's a nonlinear or non-convex least squares problem. We could probably also try to visualize this. Yeah. So if I take, for example, if I know where sensor 1 and sensor 3 is, but we have no idea where sensor 2 is, but we have these 2 distances here. So say we know this distance between 2 and 3, and we know the distance between 1 and 2. There would be 2 optimal solutions possible. Yeah. So we could place the sensor 2 here. That would satisfy this, but we could also flip it, mirror it to the other side. That would be another locally optimal solution. So this would be another locally optimal solution to this least squares optimization problem. So actually, there are mirror solutions possible, so which already shows this is a non-convex optimization problem. Yeah, so we have multiple local minima in this optimization problem, and mathematically, this really comes from the term here that we don't have the square here at the norm. That would be nicer, of course. Yeah, and well, actually, what we are going to do in this talk is we will formulate optimization problems of this form in a standard format. And in order to briefly explain how to do this, we do the following. Actually, in order to bring this to standard form, we will introduce these variables for the first and the second sensor here. So actually the first sensor keeps a copy of its own position and the position of its neighbor. So actually the theta 1 is an auxiliary variable which is fixed to He2. Yeah, so there's an additional consensus constraint. And the variable x1 is now simply the optimization variable of the first agent or of sensor 1, but it keeps a copy of the position of its neighbor. We will see in a minute why this is useful. So, but what we can do is we can keep on doing this. Yeah, so we can set x2 equals He2 theta 2. So also sensor 2 keeps a copy of the position of sensor 3, and so on. Of course, we will still we will only double the number of optimization variables if we do this. Now the new variables are these xi's. Yeah, so always the position of sensor I and its neighbor. And the reason why this is useful is actually because it helps to come up with separable objectives. So in this case, since we have a copy of our neighbor, this term is not coupled. There's no I plus 1 anymore. So all the variables are now the optimization variables xi I and theta I. They only have indices I here. Yeah, and the measurement eta I plus 1 needs, of course, to be communicated to the I sensor in order to formulate this objective. And the separable non-convex objective is really the objective of sensor I. And of course, all these coupling constraints, all these constraints that the theta I is equal to the position of the neighbor, that's a coupling constraint. But that is now affine, actually. So all the coupling is in an affine constraint, while the objective of each sensor is nonlinear. So fi of xi is a nonlinear, in this case, even non-convex function. Yeah, so the non-convexity is, of course, still there. That's not resolved. But actually, the good news is these non-convexities are now separable. Yeah, so this function f depends only on the index I, and this function only depends on the variable xi. So there's no global coupling anymore in these functions fi. But the coupling is all in this affine constraint, which could be written into this general format here. Now, the optimization problem can be written in standard format, and actually throughout this talk we will always use this notation. So it's good to keep this notation in mind. What I claim is basically that all relevant distributed optimization problems can be written in this form, basically in this general setting. Yeah, but notice that the functions fi, they may be non-convex, so that may be different to other talks you have seen around non-convex optimization, actually. Yeah, but all the coupling is affine, so that's a convex constraint, of course. So what this talk is about is really about finding local minimizers of this optimization problem. So the first part of this talk is actually on algorithm and theory development, and the second part of my talk will be on applications. Once more, the characteristics here is the fi is potentially non-convex. Yeah, so these functions map from Rn to R in general. Here in our case, it was an example from R4 to R. Yeah, so since we have two position coordinates and the copy of our neighbor, the matrices Ai and the vector B are given. And of course, the big problem is that n may be very big. The capital N may be very big. So that maybe just think of a large network that could have hundreds, thousands, or millions of agents. And actually, what I want to do in this talk is actually I would like to give a brief review of existing methods for solving such distributed optimization problems. So I will talk a bit about existing distributed optimization algorithms. I will keep this brief. Then I will go into a new type of algorithms for non-convex distributed optimization. So this will be the theory part. And then in the applications, we will talk about applications in control, sensor network optimization, identification, also model predictive control with different agents or long horizons where we would like to decouple the optimization problem and solve it on more than one processor. So let me jump right in. So actually, just recall the optimization problem that we want to solve is a coupled optimization problem, but the coupling is only in the affine constraints. The functions fi are potentially non-convex. One way to solve this optimization problem is, well, if the functions fi are convex, there are plenty of algorithms around. One of them is actually the so-called dual decomposition method. And here the main idea is to solve the dual problem rather than the primal problem. So in this case, we introduce a multiplier called lambda for the coupling constraint. and we start to write down the dual or the Lagrangian function. Yeah, so we have here the Lagrangian function, and we minimize this one over the x in order to get this function d of lambda here. That's actually the dual function, and of course minimizing this, the sum over the fi of xi subject to the constraint is if the functions fi are strictly convex, that's actually equivalent to maximizing the dual function over lambda. So that's this dual optimization problem, max over d of lambda. So actually the limitation here, or the big limitation here, is this dual optimization problem is only equivalent to the primal one if the functions are strictly convex. Well, that's not quite true, right? So there are some non-convex optimization problems where we have no duality gap, but they are rare or scarce. Yeah. So that will not work in general for the case that we have non-convex optimization problems. Yeah. So for non-convex FIs, a duality gap is possible. But nevertheless, I mean, this algorithm is actually, by the way, this is quite old. Yeah. So this has been appearing in the 1960s. Probably there are some algorithms even before that. I didn't trace it all the way back, but this is at least 50 or more years old. Optimization algorithms for convex optimization. Now, in recent years, there has been another method from the field of convex optimization, which is actually called the so-called ADMM method. I think many of you have probably heard about it, since if you're around at convex, in convex optimization conferences, also in control conferences these days, I think it's everyone is talking about the alternating direction method of multipliers. So that's actually another way to solve distributed convex optimization problems to optimality. It's an algorithm, and here, in order to solve these optimization problems, what we can do is we can develop an algorithm which proceeds as follows. So actually, this algorithm solves a decoupled nonlinear programming problem. So this is actually completely decoupled. Yeah. So we are minimizing these functions fi. And then we have here the same term as in the dual decomposition. So we have some Lagrange term which basically penalizes the direction which are fixed by the consensus constraints. And we add another term here, which is actually a so-called augmented Lagrangian term. So we add another quadratic regularization term. And then the algorithm simply proceeds by taking dual gradient steps. So it's very similar to the dual decomposition method. But at one point in time, of course, we have to communicate with our neighbors in order to make progress. So it's not enough to solve decoupled optimization problems only. At a certain point, we always have to communicate. In the case of ADMM, this is done by solving a big coupled quadratic programming problem, which is of course structured. So there we can use linear algebra tricks or to distribute these the operations which are needed to do this. But this is actually the communication step. And then the only thing we need to do is to update the iterates and keep on running this recursion. So actually, ADMM it's an extremely simple algorithm. It's extremely effective. It can be proven that if the FIs are actually convex, then this algorithm converges under very mild conditions. Yeah. So if they are strictly convex, it converges definitely under. Well, and under very mild conditions, it's also for general convex functions. We can have convergence proof. So this algorithm, by the way, it's quite old. It has already been published in 1976, but it has received a lot of recent interest, I would say. Especially there's been in 2011 there has been a paper by Stephen Boyd on this, and since then somehow everyone seems to be using this algorithm or rediscovering it. So it's an old algorithm for convex distributed optimization, which is used these days. Yeah, there's actually a question.
Yeah, Boris. So the idea is, if I see the problem in a step one and also in the dual decomposition method, the idea is that these agents would start to solve somehow different problem than they wanted to solve in the beginning. So you somehow try to make them cooperate. Just by letting them to take care about some other terms in their objective functions, right?
Yeah, that's right. So the question is about how the algorithm makes progress and how the collaboration between the agents is. So it's correct actually that the agents solve their own optimization problems. So they have of course this potentially nonlinear function here. So it's, in this case, it has to be convex in order to get a convergence proof. But actually, we have these fi's of yi, which contain, of course, a lot of information. So in the decoupled case, if there would be no consensus constraints, all agents would be done after solving this decoupled NLP. Yeah. So they only have to reach consensus if there's a coupling, and if the multipliers are non-zero, so to say, of the coupling constraint. So if the coupling is active, then yeah, we have to add these terms here in order to correct the objectives of the single agents. And indeed, the reason why progress is made is because at a certain point they're solving these coupled quadratic programming problems here in order to communicate. By the way, there's often a lot of structure in this coupled QP here, so it's sometimes possible for specially structured matrices AI to do some linear algebra tricks such that only neighbors have to communicate in order to solve this quadratic optimization problem. Yeah? So that's of course, solving this optimization problem here looks complicated, but it boils down really to linear algebra. So there's no inequality constraints. It's really just the equality constraint quadratic optimization problem. So the KKT optimality conditions for this QP here would be just a linear equation system. Okay. So what I wanted to talk about is actually the limitations of this. So there are various limitations if we look at this. So first of all, that's a general problem of both dual decomposition but also the ADMM methods. It's actually, if we start working with these methods, we find that these methods are actually very scaling dependent. So if we have a big network, the convergence rate may be very slow if the variables are not well scaled. And that's actually a huge problem. We will see this. The other thing is, and that's actually also very serious, is actually if the functions fi are non-convex, there's no guarantee that these methods converge. And we can also show this, yeah. So actually ADMM is divergent for non-convex examples. So we can easily construct a counterexample. So this optimization problem here is trivial. So I think every one of you can solve this immediately. So of course, if x1 is equal to x2, we are basically minimizing x1 squared, right? So if we would substitute x2, x1. So of course the solution is at 0, and also the Lagrange multiplier will be 0 since since this is a quadratic function which has already an unconstrained minimum at the optimal consensus problem. And so we have a unique regular minimizer. So this optimization problem is completely fine. Yeah. So there's no degeneracy. But actually, if we run ADMM, all the subproblems are strictly convex, and yet this algorithm is divergent. So for non-convex functions, fi ADMM does in general not converge. I should probably say there are these days there are a lot of people working on extensions of ADMM for non-convex problems. So some people have convergence proofs for the case that we make the rho very big. But actually the performance is not great. Yeah, so I've already mentioned that basically the convergence rate is very scaling dependent, and then there's also this tuning factor rho here for the augmented Lagrangian. So if we make this bigger, so not 3/4, I think if we choose it like 10 or 100 or so, it will probably converge very, very slowly. But that's not what we want, basically. Yeah, so we will see we will get much better performance by other algorithms which are tailored for non-convex optimization problems. So actually what this talk is doing is actually we would like to address problem 2, and in fact we will overcome problem 2. And I would also like to outline that actually the algorithm I will present is mitigating at least the problem 1, or eventually solving it partly. Yeah, so the scaling dependence issue. So and that's already it. This brings me to the second part, which is the core part of this talk today. So actually all the things in the theory we will talk about are actually on the next slide. So if you got the next slide, you probably got most of the talk. So actually, Aladin stands for an algorithm which is called the augmented Lagrangian-based alternating direction inexact Newton method. Well, that's kind of lengthy, right? But Aladin is actually the abbreviation is Aladin. So that's where this name comes from. And I would like to point out that this is actually an algorithm which is very, very similar to ADMM, but not quite. And I would like to point out some of the important differences, actually. So let us have a look. If you recall what ADMM did, it actually solved decoupled nonlinear programming problems, which looked like that, actually. Very similar to that. We solved decoupled NLPs, so this step has exactly the same cost as step 1 of the ADMM method. So we are minimizing these functions fi of yi. We have this correction term here, which depends somehow on this Lagrange multiplier. And we have an additional augmented Lagrangian term here, which is scaled by this matrix hi. I will talk about how to choose this hi in a second. We will find a way how to scale this properly. The next thing we do is actually we compute something like a gradient, but actually this method is completely derivative free that I'm going to present. So there's at no point any derivative of this function fi needed. Yeah. So this function fi could have kings or go to infinity at a certain point if there's a constraint. So all the constraints could be hidden in the fi. Yeah. So that could go to infinity. So we just compute something like a generalized gradient by using the solution. So yi is simply set to the solution of this NLP here, and then we evaluate this vector gi. The next step is actually optional. We can optionally update this matrix hi, which plays somehow the role of a Hessian matrix approximation. I would like to point out there's at no point, we assume at no point that these functions fi are differentiable. So if they are non-differentiable, well, then we can, of course, not compute the second order derivative of the fi. Yeah? But this step is really optional. It kind of should be somehow, this hi should be somehow an approximate way of it should somehow approximate the curvature of this function from a broad view. So as soon as we do this, we get the scaling right. But if it's, of course, Aladin also works for twice differentiable functions fi. In this case, we could also set hi equal to the exact Hessian matrix. So if we can compute this, that's fine. If not, then, well, we choose some approximation there. And step 3 is actually we solve a coupled quadratic programming problem. So actually also this step has exactly the same cost as the ADMM step. So there's, in terms of the iteration cost, it's exactly the same as ADMM. But there's a difference here. Yeah? So if you recall, in ADMM, we had a dual gradient step which was implemented. That's not here. Here we are only computing something like a gradient, gi, and we compute a Hessian approximation, and then we solve a coupled QP. So probably some of you are familiar with sequential quadratic programming methods. So actually, sequential quadratic programming methods are a type of optimization algorithms for nonconvex optimization, which basically solve sequentially quadratic programming problems, which look very similar to this one here. So we basically expand the objective function. We have a gradient term here, and we have a Hessian matrix approximation. So this is actually a quadratic, could be interpreted as a quadratic approximation of our objective function. And we solve this subject to this coupling constraint. I would like to point out already at this point once more, yeah, so also this coupled quadratic programming problem, which we are solving here in step 3, it is actually unconstrained. Yeah, so okay, there's this coupling equality constraint, but there are no inequality constraints. So there's nothing like an active set method or anything needed. Yeah, so this whole solving this coupled QP here again boils down to linear algebra. So the structure of the network is completely preserved in all the linear algebra operations that are needed. The only difference is actually whether we update the hi or not. So there are ups and downs of doing so. Yeah. So if we do update the hi's, well, we do get better scaling in general. But of course, for the linear algebra operations, it might help if we can pre-compute decompositions of the linear algebra steps which are needed for solving this QP. So there's a certain advantage of keeping the hi's constant for a while. And then we do the same as ADMM does. We update the variables and go back in. Now the question is, why do we do this? Yeah. So does this have any advantage compared to ADMM, or how does this relate to SQP? In order to understand this, I would like to point out a few special cases. So let us have a look at this. So first of all, if we go with the tuning parameter and make that very, very big, so if we go with rho to infinity, this algorithm has a very, very beautiful property. Namely, the Aladin iterations actually become equivalent to an SQP method. So that's actually great. Let's look at this, right? So basically, if we go with the rho to infinity, what happens is that the decoupled NLPs are useless. Because if we make that penalty here very big, the optimal solution will be to set the yi to the xi. So we are basically doing nothing in this step. Yeah, so basically we're making this quadratic penalty here very big. So basically the solution will be yi equal xi. And then, well, I mean, this other step here is we are solving this QP. So we are evaluating the gradient and we are evaluating the Hessian. And then we solve a QP and we run this in a circle. So that's an SQP method, actually. Yeah? So for rho to infinity, under some mild technical assumptions, it's equivalent to SQP. Then for the case that we have a very ugly Hessian matrix, actually, if we relate the Hessian matrix to the constraint Jacobian, in that case, somehow it turns out that Aladin is equivalent to a variant of ADMM. So in a way, we are containing ADMM as a special case. But we will see how unnatural that is, actually. So we will do much better scaling if we choose a different HIs here. And actually, the other thing is for rho equals 0 plus some additional technical assumptions, we can show that the Aladin iterates are actually equivalent to dual decomposition. So in a way, all the existing methods which are there from the convex world are kind of contained in this framework as a special case. So I think that's the main point I wanted to make on this slide here. Yeah, sure.
If I'm interrupting too much.
No, please do.
So there is an update for the lambda. You just take the Lagrange multiplier which you get from the solution of the QP.
Yes.
And but you were also solving QP in the ADMM with also that constraint.
Yes. And we throw away the lambda.
Sorry?
We throw away. I just repeat the question first. So the question was again, what is the difference between Aladin and ADMM in terms of the multiplier updates? I should probably say this once more. So actually here in the Aladin variant, we update the multiplier by choosing the multiplier here from the QP of the equality constraint. So that's our new lambda plus, and then we set lambda to the lambda plus. So that's from the QP, same as SQP methods, basically. They would do this exactly the same. Let me briefly jump back to the ADMM. So what they do is basically we are updating the dual in step 2. So instead of computing gradients or approximating a Hessian matrix, we do something like a dual gradient step here. And that's also where we lose things. Because that's basically a gradient step. So that will cause all these troubles in terms of convergence rate, in terms of scaling. Because it's basically a steepest descent method on the dual. We could interpret it like this, more or less. Yeah, so the dual is updated in a very different way in the ADMM framework. So that's the main difference, I would say.
But in principle, you can already update the ADMM just by taking the dual of this constraint there. Okay. Yeah, nice.
Yes. So yeah, I mean the difference is really in the update of the dual. Yeah. Other questions at this stage? Yeah, so basically, I think if you got this algorithm, that's basically it, right? So I mean that's all I'm talking about today. All right. So there are the special cases. Yeah, so we somehow contain different special cases. What I would like to talk about next is actually a little bit of convergence theory. So we'll talk a little bit about theory before we move on to the applications. So let me talk a little bit about the local convergence first of all. So if you recall, actually, if we talk about the convergence rate of ADMM or also dual decomposition, we get there are some papers around under some regularity assumptions we can show that ADMM converges linearly, but the rate may be very, very slow. So what we do here is actually we could analyze it under stronger regularity assumptions. So actually, the first assumption is horrible. The FIs are twice continuously differentiable. That's not the case in practice, yeah? But, I mean, let us nevertheless do this and go to step back in order to see how the convergence rate is in this case, yeah? So we'll later say how it generalizes for non-differentiable functions. The other assumption that we need, so this is pretty strong assumptions, but it gives us a very good idea about scaling, actually. So if the minimizer is a regular KKT point, so if it satisfies the linear independence constraint qualification and also the second order sufficient condition, KKT condition, and the HI is such that the decoupled NLPs are locally convex, then we can make the following statement. So the full step variant of Aladin, actually with rho equal 1, so by the way, we know how to scale the rho, converges locally with quadratic convergence rate if we use exact Hessians, yeah, or almost exact Hessians, as long as the HI somehow converge to the exact Hessian, then we can show quadratic convergence, and we get linear convergence rate if somehow the approximation is not too bad. So actually, if you recall the convergence theory of standard sequential quadratic programming, we get pretty similar results. Yeah, so basically, the local convergence theory is inherited from SQP. So I won't go through the proof today, but actually, the proof basically goes literally and says, okay, Aladin and SQP are so similar that basically we can transfer the proof. And that somehow works out, right? So we can as soon as we get the Hessian matrix more or less right, we can show that we get very good convergence rates. And of course, this also enables us to use all these kind of heuristics which have been developed over the last 50 years in SQP for all these Hessian matrix updates, right? So there are, for example, BFGS updates or Gauss-Newton Hessian approximations, right? So there are all these heuristics around in the SQP theory which tell us on how to do, for example, low-rank updates of the matrices HI. So we can do a lot of linear algebra actually in order to update HIs, and Aladin completely or fully benefits from all the SQP theory in order to get better local convergence rates. So that's I think a big step in distributed optimization. The other thing is we get local quadratic convergence actually under this condition. So if you recall my counter example for the ADMM actually, so this here's okay. I just said my assumptions are horrible, right? So my functions fi are assumed to be twice continuously differentiable, which is ugly, yeah? So that's not happening in practice. But there's no convexity assumption here. So this completely works. I mean, this method finds, it converges locally under this condition here, yeah? So, but we can show local convergence no matter whether the problem is convex or non-convex. Yeah, so that's a big difference to ADMM. Yeah, while ADMM maybe even even if we start ADMM very, very close to the locally optimal solution, it may be diverging. So that's a big step. Now, of course, I mean we could go back and ask the question, what can we say about global convergence now? Yeah, so this only says something somehow about the convergence rate and the scaling properties of Aladin. So let us go back and remove this assumption on this function fi that it's twice continuously differentiable. So here what I'm going to assume about the fi's is simply the same assumption as we have in the ADMM case. They are closed, proper, and strictly convex. So what can we say in this case? We don't know many assumptions. Yeah, so these assumptions are great, except for the fi needs to be strictly convex. Actually, we also assume that the scaling matrices HI are not updated. We can relax this assumption later on again. In this case, however, we can show that the Aladin iterates Y converge globally. So roughly from a broad perspective, we can say if we apply Aladin to a convex optimization problem, then it converges no matter what we do, basically. Yeah, so from any initialization point. So we are trying to combine the best of the two worlds, right? So this is by the way, this statement cannot be made for SQP methods. Even if we would apply an SQP method to a convex optimization problem, if we want to show that it converges from any initialization point, we would have to combine the SQP method with a line search or trust region method in order to establish convergence. No such thing is needed for Aladin. Yeah, so basically, we have, from the global perspective, we have as strong convergence proofs as ADMM, but for non-convex problems, we can show much more. So that's the basic theory that I wanted to talk about. I should probably say this. We have actually various papers around on Aladin. So the first one appeared in the Science Journal on optimization in 2016. So we published the original version of the Aladin algorithms, but now the global convergence proofs we have them in optimization online, so they are currently under submission. So it's really very recent work actually that we were able to prove this here. So you can find these results online. In the non-convex case, we can still establish something like global convergence to local minimizers. Well, this is getting a little bit technical. It's probably a little bit of detail, but I nevertheless wanted to say the main idea. is to, if we anyhow have extensions of, oh, by the way, there's a square missing here, so I wanted to make this function fi of xi convex by adding quadratic penalty. So if we can find a row such that we can make the fi strictly convex in the xi, the Aladin iterates would converge to this to the solution of this convex optimization problem here. And I mean, the main idea for enforcing global convergence in the non-convex case is basically by running a proximal method. So basically, we update the set with the set plus. So that would give us a proximal method which would converge to the solution of this convex optimization problem. And then, well, I mean, the xi is updated from time to time. In order to enforce convergence, and actually we are currently working on variants of this idea in order to have a globalization strategy for Aladin in the non-convex case. But I don't want to spend too much time on this slide actually. But it is possible. Yeah. The other thing I wanted to briefly talk about is in the case that we have distributed NLPs with inequalities. So if we want to put them, if we want to put the inequalities here, they can be decoupled, of course, since we can always put a coupling into the affine equality constraints. In this case, the assumptions on the optimization problem are all the same, with the only difference that we know of also this function's hi here. So we have in general non-convex constraints in the NLP. The rest is the same as previously. What we can do in this case is, of course, we could just replace these functions fi by new functions fi tilde, which are simply the previous objective, which is set to infinity if the constraint is infeasible and otherwise nothing is added. In this case, the derivative-free variant of Aladin is fully applicable. Yeah, so we can show still global convergence theory is valid. So we will find the local minimizer. That's no problem to do this. The only part where it gets difficult is, so to say, we also claimed that actually we have a good global, a good local convergence rate, which is of course not fully true anymore. Since if we write the inequalities explicitly into the objective function, of course this objective function will might not be differentiable anymore. So the local convergence theory becomes more difficult, but we are currently working on derivative-free BFTS variants in order to fix this. So also this is part of current research actually, what things we are working on in the moment. Okay, so I think this is pretty much all I wanted to say about the theory. Yeah, so far I've introduced the Aladin algorithm itself. I've outlined a little bit the advantages and disadvantages compared to ADMM, dual decomposition. I've already discussed a little bit the connection to SQP methods. So I would like to summarize this basically as Aladin is trying to inherit somehow the properties or the good properties of these methods. So that's also how we came up with these things. So there are still some details which are under development, but this algorithm performs extremely well in practice. And this is something I would like to outline in the second part of the talk, where we'll talk a little about applications. But I nevertheless would like to give you also the opportunity. Are there questions at this stage about the theory part so far? Yeah, there's one.
I mean, it's probably something in between the theory of applications, since I do not see this directly in the applications. I'm just thinking about the global optimization or non-convex optimization in general. I mean, I can think about many reformulations that these guys use in global optimization that would actually yield you the separable non-convex format with some linear coupling, if you use some auxiliary variables, and maybe with some constraints. So do you have also?
I should probably say this is something Aladin cannot do. I should probably, repeat the question first. Okay, so the question is actually about global optimization, whether it's possible to reformulate a global optimization problem maybe as a non-convex distributed optimization problem by putting all the non-convexities into the decoupled problems, thereby breaking down a big global optimization problem into smaller tractable global optimization problems, and then use Aladin on top and hope that we find the global minimizer. I should say this path is not a good way, at least in my opinion. Yeah. So first of all, the convergence proof of Aladin is really local. So of course, for the convex case, we can show that we converge to the global minimizer. But for non-convex problems, there's really no such guarantee. So Aladin, it may or may not work better if we solve the decoupled NLPs to global optimality. But in general, we will not find the global minimizer of the original big global optimization problem. It would also contradict all kinds of complexity theories which are around. Yeah, so if we could solve a big global optimization problem with exponential complexity by breaking it down into smaller ones, there would be something strange. Yeah, so that's too good to be true. Yeah, so there's no way to do this. Actually, I should say one warning. In fact, it's possible to construct non-convex optimization problems where we can find the global optimal solution or compute it. Yeah, so just by using the structure. And what we can show is basically that if we initialize Aladin at a given point and solve the decoupled NLPs to local optimality, we find a better local minimizer than if we solve the decoupled NLPs to global optimality. So in fact, it's even possible to show that solving the decoupled problems to global optimality actually does harm to the overall convergence properties of the algorithm. So it's in fact, yeah. So I mean, of course, in practice, what we observe is if we use Aladin with a global solver for the decoupled problems, usually the performance gets better. We find better local minima, but there are counterexamples. Yeah, so there's absolutely no guarantee. So it's completely heuristic. I should probably say a similar thing happens for ADMM. Probably some of you have talked to Stephen Boyd, who has tried this as well. So Stephen Boyd has actually tried to apply ADMM to non-convex optimization problems with limited success. So they have some papers on this around and claim that it works good, but it's if you talk to Stephen, he will tell you basically it works for very special problems, not in the general setting. So yeah, so I would like to really outline this work here. Use it for local optimization. Don't use it for global optimization. Yeah, so I really feel. I'm myself working in global optimization. We are developing global optimization algorithms. I think if you want to develop a global optimization algorithm, you should completely rethink. Throw away all the local optimization theory. Rethink from scratch. There's a completely different ways of completely different types of methods are needed, basically. So whenever we do something in local optimization, like using derivatives, that's a bad thing in global optimization because derivatives are local, right? So they contain local optimization. From a global optimization perspective, there's no need to compute derivatives. So if you have a global optimization algorithm which uses derivatives, throw it away. Okay, that's my opinion, right? So I just, yeah, okay. But so this talk is really about local optimization. I should say this. I also say this to prevent you from going into this direction because I was in contact with different researchers actually who saw the Aladin paper and then they contacted me and said like, oh, we tried to work it out for global optimization. This could be a great opportunity. I always reply, no, don't do this. Okay. All right. So next, well, are there more questions about the theory part? Yeah, there's one there.
Give an example of a function which does not have a second derivative. So like.
Oh yeah, here's one. If you have an inequality and write it into the objective, that would be non-differentiable since you're okay. Since basically the function, even if it's convex, right? So it may be not differentiable and convex, right? But then there's an inequality, so it goes to infinity since it's infeasible outside this region. So that would be non-differentiable. But I mean, another example is there are all these L1 penalties, for example, in identification. Yeah, so if you want to do sparse identification and you have a quadratic least squares term and then a L1 penalty, or a nuclear norm that you would like to add to your objective, that would be non-differentiable.
So it's from the inequality constraints.
Oh, it could be both. Yeah. So from the constraints, you would get non-differentiabilities if you write them into the objective. But it could also be part of your objective. Yeah. So nuclear norms would be. So if you want to do identification for images, for example, yeah. So face recognition, you would write some nuclear norm into your objective in order to identify something or have a sparse identification. Exactly. Yeah. So that would be an example for a non-differentiable objective. Yeah. That's a
stupid question.
Yeah.
I understand very well that if I am trying to generate a global algorithm, I don't have to use the first derivative, the Jacobian, but you are using the Hessian. What is the meaning?
Well, I'm not quite using the Hessian. Yeah. So yeah. Okay. I mean, the thing is, this step is really optional. But it helps to scale. So basically, I claim that the main disadvantage of ADMM, I think, is that completely no Hessian information is used. I think there's always some information about how your objective is curved. At least, I mean, we can do something like if we evaluate even a non-differentiable objective at different points, we can do fitting and fit a parabola through these points. As soon as we can do this, we have a rough idea about the scaling of the objective functions. And this is exactly what we are trying to use. And this is also something I tried to outline this. So even if these functions fi are non-differentiable, we can use non-differentiable methods to update the hi, like a BFGS would do this. So there are people, in fact, in non-differentiable optimization who use BFGS methods. They just use an SQP method and run it with BFGS. Sounds horrible because you're approximating an object like a second order derivative that does not even exist. But still, BFGS tends to perform surprisingly well. And this is really something you can do with Aladin. And the advantage compared to SQP is that this is justified even in the theory part. So if people do this in SQP and use BFGS, SQP on a non-differentiable objective function, works great in practice. I haven't seen any reasonable convergence proof at the moment. Maybe there are, but they are very technical. It's not quite solved, I would say. Are there other questions? Okay. Radu has a question? No. Okay. Okay. Where? Okay. Okay, let's go to the application and talk a little bit about the performance of this algorithm. So first I would like to come back to my motivating example, to the sensor network localization problem. So actually we just set up a sensor network, actually not with 7 sensors but with 25,000 sensors randomly placed just to generate a case study. And actually we can measure the positions and distances in a graph. Additionally, just to make it more fun, we have added inequality constraints. That might make sense a lot in practice, actually, because we would like to remove outliers, of course. So if we get wrong measurements, we cannot expect that all 25,000 sensors would work, right? So we would like to remove outliers, obviously. So we've added inequalities as well, which leads to a big optimization problem with 100,000 optimization variables, because each sensor has at least 4 variables, 4 degrees of freedom, its own position and a copy of its neighbor. Now here's the comparison with SQP. So actually what we see is that, well, I mean the red dots are actually the Aladin iterates, and the black triangles are the SQP iteration. So what we see is basically that the Aladin iteration, it converges with the same rate as the SQP method. So the local convergence rate is similar, but in the global phase, we will get much faster. Yeah, so we will. There's of course a benefit of solving the distributed optimization problems first. And actually, in order to understand this here, so we should also say that, of course, the iteration has almost the same cost. In practice, we would stop here actually. Yeah, at 10 to the power of -3, say. So because in practice we would like to identify with the accuracy up to 10 to the power of -3. Yeah? So I just continued the convergence plot in order to show the difference. The other big difference is, of course, actually SQP. Well, actually, I should revise what I just said. Yeah. So basically, the SQP iteration is more expensive than the Aladin iteration. Why is this? Because SQP would solve a quadratic optimization problem in every step, and this QP has inequalities. So every time the SQP method solves this QP, it has to run an active set method and redo all these linear algebra computations. While the Aladin iteration just solves an equality-constrained quadratic programming problem. So in fact, it's much faster. Yeah. So not only it's converging faster, but also the time per iteration is much faster. So that's actually a real benefit compared to SQP. Of course, what we can do in SQP is we can parallelize the function evaluation, we can parallelize the derivative evaluation, but we cannot parallelize the solution of the QP. Yeah, since we have to run an active set method in order to identify the right active set during the iteration, while Aladin does not have this problem. Okay, so this was an example with 10 to the 5 primal variables and also quite a few dual optimization variables corresponding to all those constraints. The other performance plot that I wanted to show is actually we tried that on a more industrial case study, actually on an optimal power flow problem. So actually that case study was taken from IEEE 5-node test case. We can do much bigger ones, but I mean, to get the main point, we can also do 5 nodes. We can do thousands of nodes, so it scales up easily. So this is not so much the point of the slide. I should say, actually, this work has been done with in collaboration with the Karlsruhe Institute of Technology. So together with Tim Faulwasser, he's somewhere here, I hope, and Alexander Engelmann is a PhD student at KIT. That's actually a paper we will also present at IFA conference. So actually here we have a consumer network, and there are generators and consumers in this electrical grid here. And actually what we would like to do is we would like to minimize the cost of the energy production and grid operation subject to the so-called power flow equations, which has as optimization variables basically the voltages, but we see here there's a product of these voltages. There are conductances, so the GKLs and BKLs are given parameters, so there are inductances and resistances in the lines. And actually the active and reactive power demands in the network are given. And basically there are some constraints which are not shown here. So the whole optimization problem didn't really quite fit on the slide. But what we see is these power flow networks, they're actually horribly nonlinear. So since we have these products of the voltages here, and then there's also well, I mean there's a phase angle between the AC currents which has to be taken into account. So that's another optimization variable which enters in a very nonlinear way through these power flow equations. And of course, we have to introduce again auxiliary variables in order to move all these couplings into affine constraints. That's the step we have to do. But if we do this, we end up with a big coupled nonlinear optimization problem where all the coupling is in affine constraints. And actually, in this case, what we did is actually people in engineering, they somehow already use ADMM also for non-convex optimization problems. So it seems like people in power flow networks don't care much about the theory, so they just dare to apply it to their electrical grid, which is actually completely fine. No, we shouldn't laugh, actually. No, it's actually great because it turns out it converges. Yeah, so it works. ADMM works in this case if we make the rho big enough. So that's just fine. But if we look at the performance, so we have here this index k. So we see we played around a lot actually in order to make the ADMM work. So we played around with this tuning parameter rho, and we basically see the convergence of ADMM is not really satisfying. Yeah? So we would eventually stop with 10 to the power of -3. So it would probably ADMM converges after 100 iterations or something like that. But while Aladin is like the solid line here is the Aladin iterations. Yeah? So it converges after 8-9 steps here. We are already pretty accurate. So that's much faster, and the reason is again that we have enough information in the Hessian approximations in order to speed up the convergence rate a lot after a few steps already. Yeah, and we see that Aladin here performs much better. Although in principle we could use ADMM for this case study. Yeah, so it works in principle.
Joe, the quick question:
Mm-hmm.
Is the best case results, worst case results, or the average case?
Okay, well, this was the result for this 5-node test case. So, okay, it's a little bit cheating because it's a very small scale case study. But in principle, we see the trend, right? So, I mean, I mean, we tried for bigger networks, but there are no surprises. It looks similar.
You still have some initialization possibilities, right?
Yeah. Oh, that's right. Yes. Yeah. Yeah. Okay.
Just with respect to this, I'm
yes.
questioning the size of the case study.
Well, I mean, in this test case, actually, the initialization value was also given. It's somehow a benchmark case study that we used.
Okay.
So, but yeah.
What about tuning parameters? Does some tuning parameters in Aladin have the row and the h?
In Aladin, actually, we set the row to 1. So there was absolutely no reason to tune anything. So it works completely without tuning. So in this case, we worked with exact Hessians. So there was no tuning involved. It's self-scaling, so to say. Yeah. So there was it just works out of the box.
And if you change row, could it be even better? Or?
No, actually, it's not. Since in this case, we can compute the Hessian matrices basically. So here in this case, these power flow equations. I mean, they look horrible. I mean, they are non-convex, but we can compute second-order derivatives of this guy. That's not a problem. So in this case, we can scale with exact Hessians. That hasn't been an issue here. So actually, this case is nicely smooth, so to say. So the auto scaling works. Yeah, but as I said, I mean, even if this would be non-differentiable, we are working on these BFGS variables, BFGS variants, which tend to work well. So we hope to get to a completely tuning-free framework where basically the user does not have to enter any tuning anymore, where it just works out of the box. Also, I mean, we are currently working on a software for this. So basically, the idea is, of course, to distribute all the operations. So what the user has to do is basically get her NLP solver working for the small optimization problems. And once this is working, basically the software framework should be able to put this together in order to solve this big distributed optimization problem. So that's probably also it's a different approach to what Sigurd said today in the morning, right? So we are trying to extend the optimization framework also eventually for plant-wide control. We don't have case studies for this yet, but I think it could be a path that could be viable to get there, right? So if we have all these small controllers which basically use their own NLP solver to solve small, easy optimization problems that can be made work, if Aladin is capable of bringing this together in order to solve the plant-wide optimization problem, I hope it's a path that may lead to some results or overcome all these big difficulties that we have at the moment with the centralized solvers for these big case studies. Mm-hmm. Are there other questions about this case study? So we are currently working on bigger case studies. We are working on I mean, the collaboration with KIT is still continuing. Of course, Karlsruhe Institute of Technology has a lot of industry collaborations actually with real grids. So we are trying to make that work on actual case studies in Germany on German electrical grids actually at the moment. So it's hopefully working on big case studies very soon. Okay. The other thing I haven't talked about so far, I've talked about non-convex optimization, in fact. Yeah, so we had this sensor localization problem, which is a non-convex least squares optimization problem. I've also talked about this big electrical grid where we did the non-convex optimization with Aladin. What I would like to talk briefly about is how Aladin performs for convex optimization problems. That's actually interesting since we claim that we can compare or compete with methods like dual decomposition and ADMM. So here we set up a test problem which actually, that's actually the example I just mentioned for a non-differentiable objective function. Actually here we have added the one norm of the x in order to do a identification problem or sparse identification. So that's the standard lasso formulation where we want to minimize this. So that's a completely convex objective, of course. They're just norms, right? So there's a one norm here and the two norms squared. So in this case, what we can do is we can simply set f1 to the least squares term and f2 to that one norm term. So we have two objectives here. It turns out that we can run the ADMM. We can work out the ADMM iterations explicitly. That's something but it's actually published by Stephen Boyd and his co-workers, right? So they have developed this explicit variant of ADMM for lasso problems. It's an extremely simple algorithm which can be implemented with 3 lines of code. I would like to encourage you also to try it out, because it's really simple. If you open MATLAB, you can implement this in 5 minutes basically. So it's a very simple ADMM iteration which can be implemented very easily. What I wanted to do is actually I would like to say that with Aladin it's as simple to implement this for the lasso problem. So if we do this with Aladin, actually we get one line code more that we needed in order to implement this. But actually it turns out the matrices here repeat. So once we have computed this inverse, they can be reused all the time. So all the linear algebra can be prepared. So the iteration cost is almost the same as ADMM, and we run these 2 algorithms in competition to each other. So what we did here is actually we generated random lasso examples, 1,000 randomly generated test scenarios with local tolerance of 10 to the power of -8. So that's the termination tolerance of the algorithm. With ADMM, we needed on average something like 310 plus minus 27 iterations. So it was for these 1,000 randomly generated case studies. And with Aladin, less than 1/2 of the iterations is needed on average. Yeah, so of course this is run on a big number of test cases. Both algorithms converge very reliably, so that's no problem. But the number of iteration matters. Yeah, so basically, and actually in this case we ran Aladin without any HI updates. So we did not update the matrices HI in any way. We just choose a constant matrix HI. Actually, if we update the HI, Aladin performs even much better than that. So we can be much faster. So also on convex lasso problems, we can compete really with these convex optimization solvers. Okay, so that's a little bit the outline on the convex optimization part. So actually, I think this workshop was supposed to be an MPC workshop. I didn't talk much about MPC so far. Sorry about that. But the last part I will. Actually, of course, we can also use Aladin in order to solve model predictive control problems. Let me briefly talk about this. So actually, in general, for nonlinear MPC, just to recall once more the problem formulation here. So what we would usually do is we would wait for the measurement x hat, then solve an optimization problem actually, which is in general a nonlinear and non-convex optimization problem here. Which runs usually over a long prediction horizon. So this I runs here up to it seems that the prediction horizon is called M here. And we may have a terminal cost as well in our objective formulation, so that L is the stage cost and M is the terminal cost, and we may have a nonlinear differential equation here. And usually we will set the initial value to our current state measurement or estimate of if we combine it with a filter in order to get x hat. And we send the U0 to the process and repeat this loop in order to close the loop. So, of course, there's a lot of theory about whether this type of model predictive controllers is stable or not. That's something I will talk about less in this presentation, actually, since I'm interested in how to solve this optimization problem online and with very, very fast sampling times. So, and in order to do this, I would like to outline first a little bit what we did in the past in order to solve these optimization problems, and also to say a little bit about what the performance is, what the numerical performance is, if we really go to actual industrial case studies. So, as Michael mentioned, a few years back, actually in 2009, 10 or so, we started to develop a tool called the Arcado toolkit. It's a software written in C++ for solving optimal control problems, and it has a very nice user interface to set up optimal control and model predictive control problems. And what this tool does is actually, at that time, like 6-7 years ago, we didn't work on distributed optimization yet. So we used centralized solvers in order to solve model predictive control problems. So what we did at that time is basically we implemented the C++ code and we did so by operator overloading in order to do something like symbolic structure detection. So we detect the structure of the optimal control problem and then try to use the structure in all the linear algebra operations and derivative computations which are going on. Actually, the way Arcado works, it's basically using a discretization scheme based on multiple shooting, and it uses a real-time Gauss-Newton variant developed by Moritz Steele, which is combined with an online active set solver for the QPs. And actually, what Arcado does is basically it takes the problem formulation from the user. So we set up MPC problems like this one here. We type them in C++. Yeah, so this looks, of course, well, it looks very close to the mathematical formulation. So the Arcado syntax, we try to basically copy the math formulation so that we make it really easy for the user to enter these optimization problems. And then what Arcado does, it does all the structure detection, algorithm development, and then writes out the MPC code, the real code that has to run online in order to close the loop. It writes it out as optimized C code. So actually at this C code, you don't want to look at it because it basically looks like static C code, right? So it's like with hard-coded indices and stuff like that, right? It's auto-generated. You don't have to look at it. It basically generates a big C file, hopefully not too big to be compiled and stored on your hardware. And this C code can be compiled onto chips like FPGAs or these all kinds of hardware chips which can be used online or on board. Yeah, so if we have something like these quadcopters or so we can have online chips in order to not take the full computer with us. And what the C code does is it simply gets us as the input the x0 and outputs the optimal decision u0 star by solving the MPC problem in an optimized way very, very quickly. So that's what Arcado Toolkit does. And in order to see a bit what the performance was like 6-7 years ago, we did that, right? So at that time, we ran Arcado on a non-distributed setting. So that was just on a standard computer. For a chemical engineering problem with 4 states and 2 controls, it's actually a continuously stirred reactor with 2 substances A and B. We see the concentrations here. It's a nonlinear reaction somehow that is going on, and we're trying to solve that tracking problem with MPC. I think the horizon was, I don't know, 10, 100, 20, 22, I think was the horizon, but that doesn't really matter here. Basically, what we are trying to look at is the computation times that we get with the Arcado code generation. So these pictures just show basically the MPC controller works and stabilizes the system as it's supposed to do. But what's more interesting for this talk is actually the computation time, since we are really talking about the algorithmic development here. So what we see like 6-7 years ago, we got computation times in the range of 180 microseconds. So most of the time is actually spent in the integration and sensitivity computation. But also the QP takes quite a bit of time. Yeah, so in this case, we used QP Oasis, which is actually an active set QP solver or an online variant of that in order to reach these computation times, which is pretty feasible for systems with 4 states, 2 controls. If you use Arcado on, we have them running on some, for example, model predictive control of kites, which have more like 22, 24 states and something like 4 or 5 control inputs. In that case, you would probably get runtimes in the range of 1 to 10 milliseconds, something like that. So if you would scale it up to 20 states, 5 variables, something like that. So if you want to run that on bigger case studies, that's completely feasible. But of course, the computation times are not that great anymore. I mean, if it's between 1 and 10 milliseconds, you would be still okay for most mechanical systems. But if it goes over that, of course, the sampling time starts to be preventive, right? So I mean, if we want to scale up a little bit further or do a bit more complicated methods, we run into the limitations of MPC that also Sigurd mentioned, right? So as soon as the models get more complex on a big chemical network, that would of course be a problem where we rather have thousands of states maybe. That could be troublesome. Okay, so that's the old stuff, right? So that's 6-7 years ago. I would like to outline a bit what we can do these days with Aladin. First of all, if we solve the MPC problem with Aladin, what we have to do is we actually in this case what we did is we don't distribute quite yet in the state space, but here we just distribute in time. what we try to do is actually to solve model predictive control problems on shorter horizons, such that we don't have to solve the big optimization problem, but just chunk it up in time into smaller optimization problems. We can do so by choosing a smaller horizon. So we divide this by capital M. The big horizon was M, and then we divide by the number of cores that we have on our machine, and get this little n here. Which is the horizon of the shorter MPC problem. And what you're looking at here is basically, don't look at it, there are too many indices, right? So that's just the augmented Lagrangian problem. That's the decoupled NLP that we are solving. Now, step 2 is, of course, on the one hand, we have to solve now these shorter horizon MPC problems. They are the decoupled NLPs in the Aladin framework. The other thing that we have to do is we have to solve this big QP on top. And the way we do this is actually these QPs, as mentioned. Yeah. So if we have Aladin, we have actually an equality constrained quadratic programming problem, which has So basically, our QP is an LQR problem, since we have this time coupling structure. So we can use the LQR theory in order to get an efficient solver for that QP. And I hope that you know LQR. Yeah. So basically, LQR problems can be solved by solving a matrix valued Riccati equation offline. So the basic idea is to propagate backwards the cost to go function. So we compute all these matrices for the shape of the cost to go function offline. And then the QP can be solved by basically matrix vector operations. So by a simple backward forward sweep. And what we can do is we can export all these operations, these online operations, as optimized C code. And for the NLP solver, we can do something like explicit MPC, or at least a rough heuristic of those. I'll talk about explicit MPC on one of the next slides once more. I first want to do the nonlinear case study just to compare the computation times to the previous what we got. What we also do is actually we run a real-time variant of Aladin. So here we only run one Aladin iteration per sampling time and skip the globalization, just to make it simple. Yeah, so we have no convergence guarantee, but that's fine. It works. So of course, in terms of the control performance, we are not talking about it. We get exactly the same. Yeah, so we are solving still the same MPC problem. This time there's a real-time variant, but it makes almost no difference. So in terms of control performance, that's just the same. Here's the computation times that we get. So recall the previous Arcado solution with the centralized solver. We had actually we got a runtime of 180. Microseconds. Here we are pretty much down to 11 microseconds with the MPC solver, with the distributed Aladin MPC solver. So again, optimized C code. Of course, we have used Arcado in the background in order to solve the small scale NLPs or the code export version of those. So now here the computation times, of course, are changing a little bit. So the QP sweeps are now much cheaper. So that's really the advantage of Aladin, is we have no inequality. So before, actually, if we solve this big coupled QP with the inequalities involved, we need 59 microseconds in order to solve that. Now we are down to 3 microseconds because we have no inequality constraint, so we can just do this backward forward sweep for the LQR solver. So that's really fast matrix vector multiplications, which can be written out as optimized C code. Actually, one down part is, of course, in this case we use 10 processes in order to get this computation time. So from that perspective, the comparison is not completely fair. Yeah. So we would have to multiply the 11 with 10, but then we get 110 microseconds, which is still faster than the 180 microseconds. Yeah, so we also perform a little bit better, but the previous one could not be distributed. So in a way, it can be distributed here. So we ran it on 10 processors. We should admit this, of course. Okay, so that's basically the computation times that we get. A little bit the down part is actually, so this communication overhead. I've tried this on basically it was a computer where we had these 10 processors connected. We measured actually 2 microseconds communication overhead just to send data from one to the other processors. I'm sure here are hardware experts who can do that faster, but it was not optimized for this. Yeah, so it was just a standard desktop computer with 10 processors, basically. All right, so that's basically the nonlinear case study. I also wanted to outline a work that I did together with Juraj and Michael on explicit MPC. So one thing we can, of course, now do is if we have a if we have a linear quadratic model predictive control problem, where we just have a linear system. So in this case, we have we took a very simple linear discrete time system. It's a very simple case study, but still, if we add constraints, it gets non-trivial. In fact, it's just a double integrator, but still, if it has constraints, it gets non-trivial. We introduce state constraints here and also control bounds, and choose some weights. So it's just the standard MPC formulation. So this is just a weighting matrix for there's a quadratic term like x transpose qx in the objective, and also for the controls same notation as for LQR. So we set up a linear quadratic MPC problem with polytopic inequality constraints, and now we can of course run Aladin. What we can do in this case is actually we can overcome one of the big limitations of explicit MPC. So if we talk about explicit MPC, the idea is actually that we enumerate all the regions that can come up if we take all the inequalities into account. So that's actually pretty feasible for short horizons, since there are not so many possibilities about which constraints can become active, and there are very efficient solvers by Michael Kwasnica and other people, co-workers, who have developed the so-called multiparametric toolbox, so the MPT toolbox, which can compute these regions for solving small-scale linear quadratic MPC problems with inequality constraints. But the big limitations there of this explicit MPC solvers is as soon as we scale up, either in both actually in state, but even more severely in time, if we have longer prediction horizon, the number of regions may explode. And one of the exciting parts with Aladin was actually that we can now break down the big MPC problem into smaller MPC problems, which in turn can be solved by these explicit solvers in a very, very efficient way. And that's exactly what we did with Juraj and Michael. So here we applied this to this very simple case study. We are currently working on bigger ones. So the first thing we did is actually, so with the real-time variant of Aladin plus the explicit MPC solver in the MPT toolbox led actually for, in this case, to 51 critical regions, and we needed 85 kilobyte in order to store those. And actually, this result is now really independent of the horizon length. So if we make the horizon longer, we of course need exactly the same storage and exactly the same number of critical regions, because the communication is taken care of by Aladin. So that's not part of the MPT toolbox anymore. So the MPT toolbox is really only solving the decoupled short horizon MPC problems. And if we put this into relation to standard explicit MPC, so without distributing, so that's of course the competitor which we would have to have in mind. We see basically that the number of regions and also the memory footprint depends very much on the horizon length. So what we see here is that for a horizon of 10 steps into the future, the number of regions is already 347. So that's already much more than the 51 regions that we have with Aladin plus the MPT toolbox. And then of course it doesn't scale that great if we make the horizon longer. So here for this simple as said, this is a very simple double integrator system with constraints, so it's still very feasible to solve this with MPT, also for longer horizons. But as soon as we scale this up to a little bit more complicated systems, I think you all know if we make the horizon longer, this number of regions and also the memory footprint explodes very, very quickly with the horizon lengths. So that's actually to put these things into relation, I think. I hope I got that right, Juraj. I think yeah.
Who helped us with the implementation.
Uning helped also, yeah. So one of my PhD students also helped with the implementation of this. But feel free to add something, because Juraj was the one who did this case study. Actually, I talk about your work. Okay. Are there questions about this part actually? Okay. Yeah, okay. I also show the performance. So actually, in this case, the reason why we show the performance is actually because we ran a real-time variant of Aladin. So we did a little bit of cheating. We don't solve the QP problems to optimality, but actually we run the real-time variant. So which means we just solve the short NLP, the short MPC problems, and then we do a communication step, and then we already move on to the next sampling time. So we take the next measurement into account in order to be really fast. But actually, I'm not sure whether we can see this actually. I think the plot is almost indistinguishable now. There's supposed to be I guess a solid and a dashed line, but they're basically coinciding, which means the two solvers have no difference, right? So for that case study, basically, it didn't matter whether we run the real-time variant of Aladin or the exact MPT solver. But actually, it's possible if we play around. I think Juraj and Üning worked on this. So if we play around with the initial values, we can find case studies where we actually see a little bit of difference in the control performance. So actually, this can be fixed by running more than one Aladin iteration, of course. Yeah? So if we solve like 2 or 3 Aladin steps in per sampling time, we could fix this. We could fix this, but this is just to show the difference. I should perhaps also advertise. So actually, yeah. So here's that's Juraj, Üning, myself, and Michael have published this in the IFAC proceedings, or are about to publish this in the IFAC proceedings. So we will. I think Juraj will present in Toulouse in much more detail. Okay. All right. Yeah, I think I'm already through. I think I'm faster than expected, in fact. So we have plenty of time for questions, but let me go briefly through the conclusions of this talk, and then also give you more time for questions, actually. So what I tried to point out in this talk is actually there's really this really new solver called Aladin, which we published in 2016. So it's really very recent work. I do this together with my PhD student Üning Zhang, and we've published this in the Science Journal of Optimization in 2016, the basic solver, and we are now publishing actually or working on a lot of updates and refinements applications of the solver. What I tried to outline is actually that Aladin can solve non-convex distributed optimization problems to local optimality. So as Rado pointed out, the word local here is really, really important. Yeah, so it's not global optimality, just once more. But still, this is surprising because if we use other distributed optimization solvers from the convex optimization world, they eventually diverge for these non-convex optimization problems, where we can get a very consistent and beautiful convergence theory for Aladin. The other thing that I found especially appealing about this algorithm is that it contains basically everything else as a special case. So it contains SQP as a special case for the situation that this penalty parameter rho goes to infinity. You wouldn't do this in practice, right? So it makes no sense to tune towards SQP, then we would lose the advantage of distributing. But in principle, it contains SQP theory as a special case, but it fully benefits from all these SQP theory in terms of the local convergence rates, Hessian matrix updates, which can be used for Aladin, like I mentioned BFGS updates as an example. It also contains the convex solvers like ADMM and dual decomposition as special cases if we do some weird tuning. Well, I mean, as I just said that. So basically, the local convergence analysis is similar to SQP, and globalization is very much possible. By the way, not even needed. So I think we ran many. We already solved many non-convex optimization problems without any tuning, without any globalization routine. In fact, without any major tricks, and just run Aladin in the full step variant in order to get local minimizers. It works just great. In terms of the applications, I think I discussed various applications time to say a little bit about the performance and advantages of Aladin. One thing I really want to point out is that for large-scale distributed sensor networks, we have seen that Aladin outperforms SQP. That's perhaps not so surprising because SQP is a centralized solver. So of course we win something by distributing the operations. But it also wins against ADMM. We have shown this on various case studies. Yeah, so we have shown it for the lasso problem, where we applied it to a convex least squares plus 1 norm type of objective functions. But we've also compared Aladin versus ADMM for that optimal power flow test case study, where we see that we get major advantages in terms of the convergence properties and computation time of the algorithm. The other thing I tried to say is basically that Aladin can be used to do exciting things in the field of model predictive control. I think it can, on the long run, be an answer to this plant-wide control problem. As at least we are trying to work in this direction. Sigurd may contradict me, but I think it's definitely. I fully agree with you that we should move away from centralized. I think we get as far. Whether we use optimization or not, that's a different story. But I think Aladin opens at least the door towards using optimization for large-scale network optimization, or also big chemical plants. The other thing I tried to say, so we worked on one hand on these large-scale distributed. Aladin does not only have advantages for large-scale distributed. That may be the first application you have in mind if you hear the keyword parallelization or distributed, but it also has certain advantages for small-scale applications in embedded MPC. For example, Aladin can be used to to alternate between explicit and online MPC. So trying again to get the best of both worlds. Yeah. So just recall there's basically I would say over the last 15-20 years there's been a big discussion about online versus explicit MPC. I'm not sure who's on which side and who wants to do what. But basically the key message here is there's no reason to stick to either explicit or online. I think this can be combined in order to use a bit of both worlds. Yeah. So certainly the advantage of explicit MPC is that everything can be stored, computed offline. There are no runtime issues. Everything can be computed. It can be stored static. So there are no memory leaks possible. It's completely static code with guaranteed runtime. While online MPC seems to perform better for large-scale problems, that has been the case because explicit MPC runs into limitations in terms of scaling up the state dimensions, control dimensions, but also, most importantly, the length of the prediction horizon, where we get huge numbers of critical regions. And I really believe that Aladin could be a way to overcome this limitation in explicit MPC. It's of course halfway cheating because then we get an online solver. It's still iterative, but the real-time iteration seems to work great. And I think at least Juraj and Michael, I think are from the explicit MPC community and are convinced that this is a good idea. At least they dare to publish with us on this topic. So that's a little bit the messages I want to get across. I have a number of references, I think. Yeah, so I think that's the paper I mentioned, the original one which I published together with Moritz and Yannick on the original Aladin algorithm. Actually, at that time we published a derivative-based optimization algorithm, but we found later that it can be modified a little bit in order to get a derivative-free algorithm, which has then been published actually, or which is available in this paper here, which is now online. And basically we've worked a lot on control. So actually this one here we have used Aladin on for parallelizable direct optimal control. And I think I also showed already some work that we are about to show in more detail at IFA conference. So that was the collaboration with KIT on distributed power flow problems. Parallel explicit MPC for hardware with limited memory is the work that I did with Michael and Juraj. There are actually many more applications that we currently do. We have currently a collaboration with Chalmers University. They are working on control of cars on intersections, actually. So they are currently building this in Chalmers University, and they are currently using Aladin to communicate between different cars in order to control them in intersections. It's actually quite spectacular because the cars go with 80 kilometers per hour over the intersection and they cross each other. So it looks quite scary, but with optimal control, it's possible to do this. And of course, distributed computations are needed. And yeah, I think we will also present this at IFAC. We have already preliminary work on this online, but we are currently continuing this collaboration. Another work actually in this direction, which we currently do with KU Leuven, is also Uning is involved in this, is to work actually on chemical processes where we have where we care about robustness. So we have stochastic variables entering, where we have these scenarios, or we want to work out different scenarios. Also there, we would like to reach consensus. So basically, the scenarios can be can compute different control decisions by themselves. So these are the distributed optimization problems, but then they want to reach consensus because they have to do. We have to decide about using one control for all these scenarios if we want to robustify. So that's something that's currently going on with the group of Jan van Impe in Leuven. Yeah, there are hopefully many more to come. You're of course also invited to join this research direction. Or I hope I could inspire you to join this exciting topic. I'm really looking forward to collaborations. I'm myself very much open to working in this direction. So we'll push this a lot in the next years to move in the direction of non-convex distributed optimization together with my PhD students at the moment. Okay, yeah, I think I'm very much in time actually. You will be soon very free to go to the mountains, I think. But first of all, are there other questions about this talk? I think we have still half an hour, if you like, or we don't.
Yeah, probably.
Yeah.
I have a question. Again, my name is Paolo Beccorelli. I come from the University of Lüneburg, Leuven. We have a project concerning the electrical auto. Typically, we are trying, or we want to try, to implement the 2 points boundary optimization problem. What do you think? Could be an idea to implement or to use your algorithms?
Okay, so first repeat the question if I got it right. It's about the boundary optimal control.
Defined in 2 points boundary optimization problem.
Right.
We have to travel from Lüneburg to München, and then we have to optimize basically the velocity.
Yeah, I think that's a perfect example. So I just repeat. So the example is to go from one to another city and basically optimize the whole procedure. Right. So that would be a boundary control problem for sure. That's a perfect example for distributed optimization. If you think a bit about this, it's something we've been thinking about this a lot. So actually, sometimes we have this global view that we want to get from one city to another city, but it might not matter so much for this big plan to figure out what's going on in some city in between, how you have to exactly turn your wheels, right? So that would be different levels of detail which you would need, and I think that distributed optimization can help there actually, because these, optimizing one section of the path that you have to go, or the control actions which are needed on one section of this path, may have not so much to do with the other sections. So that's exactly this type of applications where we see that. Distributed optimization is useful because these problems are almost decoupled, right? So you could almost optimize a control action for each of these sections. And then the question is whether we would need at all consensus actually between these sections. But it's
that you have many constraints now,
yeah.
About battery, about we can imagine the problem in this sense. The optimization aspect is extremely complex.
Yeah. Yeah, so exactly. Yeah, I mean that's exactly the applications that we have in mind. So in this case, we would indeed formulate all these constraints on different sections of the street, for example, as affine coupling constraints in order to match the variables. And then there can be a complex model even for batteries and everything on these small sections, which are then tractable because it's just a small
range extender inside when we have to switch off, when we have to switch on. The range extender for the battery. We have many complex constraints in the sense.
Yeah, no, but the battery is a perfect constraint because that's actually a coupled one. So you might run out of battery if you use too much on each of the sections. So that's actually what I mean. I would call this a resource constraint actually. So that's usually something that is fine in all the variables. It's just the power that is consumed on the section, and the sum of the power that you consume in each of the section has to be bounded or is given basically by whatever you charge at the station. So that would be the fine coupling constraint, but the particular dynamics on each of the section may be quite independent. So there are on the one hand coupling constraints, but on the other hand parts of the dynamics or parts of the decision which happen online and which do not need to be taken into account. And that's exactly why we would like to distribute. So actually in this case we have these optimization problems here where basically all the details are hidden in this function fi. And then on the outer level, we can really focus on, say, on this battery constraint, on this resource constraint which we have. So the Aladin solver is really sitting on a higher level, I would say, right? So I mean, there are all these small-scale optimal control problems which you can solve on the way, but there's this big higher-level decision-making on the whole complex task, which can be solved by these distributed optimization solvers on top. So that's basically how I would view it from the distributed optimization perspective.
Thank you.
Mm-hmm.
When you have one thing is the Aladin, the algorithm of the Aladin, but then in addition you have the software. It's not so clear to me how, where you're doing most of the work, or what's really the secret of making it work. So for example, you have the nonlinear programming for each problem. Mm-hmm. So I mean, there are many options for how you could solve this problem.
Mm-hmm. Yes, exactly. So in a way, we consider the small scale optimization pretty much solved. So which may not be true, yeah. But it's one perspective which we have, or which at least in the optimal control context, if we use Arcado on small scale control problems, even nonlinear models, this works just fine. At least if we have good initializations. So if as soon as the model is not too complicated or it's somehow a small scale situation, that just works. So that's not something we care about too much. So what we care about is about the scale up basically, and that's indeed where all the magic comes in. Yeah. So far what we've been doing. I mean, certainly the SciEM paper here. That's certainly theory, right? So I mean, it's a math journal. But now we are moving more and more back to applications. So, I mean, what we cared about first was to get the theory somehow right, the convergence, what do we do with these non-convex problems. But we are moving more and more to applications. That's also why we do all these collaborations at the moment in order to get more and more case studies in, actually, to learn about the difficulties which come up in practice. What we try to do at the moment is with the software, we are still undecided how to do it, in fact, because it's a lot of interfacing work, in fact. We would like to give the freedom to the user to use her software for solving these small scale problems, because I think everyone, depending on the application, will use something different. But we are trying to bring things together on this Aladin framework to basically link solvers which already work for the small scale problems, and then Aladin can be used as a framework to patch things together. So that's pretty much the idea. So my PhD student is currently working on this and is in contact with a lot of people who work on real problems actually, in order to figure out how they would like to implement their case study actually, or what are their requirements to do this. At the moment, it's still running very much on one computer with many processors, so we haven't really scaled up. But of course, on the long run, the idea is really to go to actual distributed systems where we also have to deal with communication delays, and of course also or to run things on a cluster, for example. But I mean, we are very open to feedback and ideas in this direction as well. I mean, if you have like ideas or case studies from chemical engineering where we can see how these interfaces would have to look like in order to be able at all to get something running in this direction, that would help a lot actually. So we are at the moment designing the software solution for this, I would say. So the software is not online yet. We just have prototypes and ideas drafting at the moment, or at least my PhD students are every day on the whiteboard doing this basically and trying to develop block diagrams to see how things could work. But what we see basically with Aladin is that we can make it pretty much work if we if we work a lot on one problem formulation, it works great, right? So you get the case study working, but then if you go to the next case study, you have again to do a lot of things in the detail in order to get it working. So we would like to reach really a state where this gets much more robust, where it's more plug and play. So we just plug the solver and then things are working out. So that's pretty much the robustest stage at which we are trying to head for. In terms of software development, I think the key is really, I mean, at the moment what we are working on is really to collect case studies from real practical engineering examples, because I mean we basically for the software development we need a huge benchmark collection in order to be able to do something useful. I mean, otherwise it won't be successful. It's also what we saw in the Arcado development. Basically, the solver was working pretty quickly, but then the real work was when people from industry came to us and had their problem and it wasn't working. So it was of course a lot of tuning, refinement, debugging. I think that's the really important stage during the software development, which will take place over the next years. I mean, it's not something that happens in one day to get us out.
Yeah. We mentioned the large-scale process optimization. I think it would be great to get the tool, but I think it's still going to be a long way because,
of course,
also because of we have all these thermodynamic equations. You have a number of phases changing, you don't know. So it's basically the structure of the equations are changing, making non-continuous.
Yeah, that's a good point.
Not continuous, but non-differentiable or locally things that's happening, and then you usually depend on local solvers which fail suddenly without. Which you don't have control over, and I mean, obviously there's lots of possibilities to do things here in this area. I think it's, but a lot of that goes into the nonlinear program, the local solve that you said is solved. I think it's not necessarily solved in many of these problems.
It's the question of think of how much we can break down things. So as soon as you break down things to smaller problems, at a certain point you will be able to solve them with your nonlinear programming solver. So that's the hope that we have, so to say, that things that we can break down things to easy solvable problems, and once we can solve all these little small problems, that it's easy to patch them together. At least that's the hope that we have at the moment. But I completely agree that with the structure changes or also events that are happening in the network, that's of course a completely new story that I didn't talk about. So I don't want to say that this solves the all these problems, right? So I mean there's of course, I mean what we did here is basically we didn't even change the capital N, which will definitely happen in real networks. We already see this for this traffic coordination problem. I mean what they have is that the cars are coming into the network, kind of registering at the intersection. But of course, the number of cars changes all the time. So there are new cars coming in. Some people leave the intersection again and unplug the network. So the number of agents in the system is changing all the time. So also this is something I haven't talked about here at all. So there are definitely plenty of challenges that we haven't addressed. But I think what I wanted to say with this one is basically there's development going on that these solvers will start to work for non-convex optimization problem, which I think is at least a big step in the direction of making such things work. Mm-hmm. Other questions, comments? Everyone wants to go to the mountains? Okay. Yeah, I think we have. We have 3:45, so I think I will stop here. I would like to thank you really all for listening to my talk, for not being in the mountains, and also for helping so much with questions, which were really great actually to get the atmosphere right here. I think so. Thank you very much, and see you around. Thanks.